Good morning, everyone. Thank you for joining us today for the webinar. My name is Adam Christofides. I'm one of the product managers here at ControlLogic. Today, Adam Rickards, who is our solution architect, is going to take us through the topic of redundancy and having a look at redundancy within industrial networks. If you have questions during the presentation, please enter them in the chat window on the right of your screen. Once you have entered in your chat information, your chat questions, I will save them till the end, and we will have 15 minutes at the end of the presentation to cover those questions. I'm going to hand over to Adam Rickards now, who's going to present. So let me just hand over to Adam. Okay, thanks, Adam.
I think it's handed to my side if you hand it over. All right, guys, thank you very much for joining us today. We're here talking about redundancy in industrial networks with a focus on standardization or standardized redundancy. And without too much ado, we'll hop straight in. From an agenda point of view, we have a brief discussion about proprietary versus standardization, a talk about timings and measuring redundancy, and then we'll go through a number of protocols and how to join those protocols together, and then we'll stop for our questions and answers. One of the reasons standardization, at least in redundancy, is so important these days is because there's a huge amount of proprietary, non-compatible redundancy solutions from many vendors. If you open any automation magazine and flick through there, you probably see 60 different industrial Ethernet vendors, 60 different protocols, all promising you different things, none of which work together. So it doesn't really lead for a good solution for a customer when if they put in something from a single vendor and something goes awry, they have to replace everything, for instance. So a bit of a move has been made to try to create an industrial standard that can be supported by multiple vendors for interoperability reasons between vendors. So a site could standardize on this technology rather than on a vendor, and it would give them a bit more freedom. The technology that's really being used in that regard is IEC MRP. We'll talk a bit about that later on. There are a number of standardized redundancy solutions available. And I'll just grab my drawing icon. We can have a look at spanning tree and rapid spanning tree. At least the earlier implementations are pretty much obsolete. Most people will be using optimized rapid spanning tree. You can see that's been around since 2010, so it's pretty mature and more or less used in most new products. And it's a pretty nice protocol. We'll go into the exact details of it, but you can see that it offers some pretty good timings, but the redundancy timing scales with the number of devices. We've got these three guys here, and to be honest, the only place I've ever seen these listed is in this table. I've never seen anybody using these protocols. So we're not going to focus too much on them today, as I honestly couldn't tell you where they're being used or what they're used for. So we'll just get rid of those. We have MRP, or IEC MRP, and fast MRP, which we'll cover today. It's a ring-based standardized redundancy. And then HSR and PRP, which, even though they've been around since 2010, more or less feel very new compared to the rest of them. And there's not a high level of understanding and knowledge from people about what they are and what they're used for. When we are talking about recovery times, it's important to note that different companies will claim different timings and not really show you how they got to that timing. When we're talking about redundancy times, at least today, we'll be talking about the redundancy time where a device in this network may be talking to a device either plugged into this switch or perhaps to a device in another part of the network. And it's when this device down here can communicate again to one of the other devices. We're not talking about how long it takes for the switches to realize, oh, there's a problem, we need to fix it, or how long that process takes to recover, but really how long the end devices will take to talk again to the end devices. So how long it will take for your application to recover. Just to cover a little bit about how redundancy works, at least in an Ethernet setting, there's more or less two important processes that have to happen, regardless of which redundancy protocol we're talking about. And the first one is to reestablish a physical communications path, and then to reestablish the logical network connections. Each protocol you come across may do this in a different way. They have a different process for executing these goals, but they still have to achieve those goals. If we look at the redundancy method for restoring the physical communications, we have here a simple ring architecture, and this could be any number of protocols, either open or proprietary. They'll have a number of links between switches. You can see here we have 5 switches labeled A, B, C, D, and E. And there is a redundant connection displayed with a dotted path, which is physically connected but not logically active. So when everything's working normally, data from this PC in the top left will travel down to the PC in the top right, and it will not be able to pass this link because it is redundant. That means the data has to pass this way to get down to PC2. Now, if something was to go wrong in the network, say a break between B and C, obviously the path between PC1 and PC2 has now been broken. They can no longer communicate. And so, at least from a physical point of view, we have to connect this link back up so that it's operating again. But if you think about the logical communications path we had before, where PC1 is talking to PC2, switch B, it should know, because it's directly connected to the fault, that there's something went wrong, but switch D has no idea what's happening. He doesn't, from his point of view, nothing changed. None of his directly connected paths changed. How is he going to know that this link on the left is broken? So each redundancy mechanism has a process for also updating the switches about what's happening. They all have different terminologies for this, but more or less, the switches tell each other, hey, something went wrong. Please forget everything you used to know about the network and relearn it again. So as PC1 is trying to find PC2, when switch B is told, hey, forget everything you know, he deletes the entry, and switch D does the same, saying, look, we used to know where PC1 and PC2 were located. We're going to forget all of that. We're going to start again. What will actually happen is the next time they communicate, switch B will send it out all ports. Obviously not this one if it's down, but assume any other ports here. And it will travel around the network, out all the ports, and eventually PC2 will receive it and it will respond. And when PC2 responds, the data will flow into switch D, and switch D will learn. Oh, sorry about that. Will learn where that data came from. So when the PC1's data comes through, switch D would learn behind port 2, we have PC1. And when PC2 responds, it will learn whichever the port number here is PC2. And the network will be restored. And that's the logical fix to the network. So the tables and databases and all the switches need to be updated so that everybody knows where everybody's now located. It could be for some devices that the entry becomes the same again. It gets put back in there. But since we don't know and we don't want to take the time to calculate where the break was and what happened in the network, we simply say, forget everything, learn it again. This is often referred to as a flush FDB or flush of the forwarding database. If we look at rapid spanning tree or optimized rapid spanning tree, it's a very common protocol. It's more or less supported in every device. And the reason for that isn't because everyone said rapid spanning tree is the best, let's all implement that, that'll be fantastic. It's because the actual chipsets from the vendors that make the switching chips come with support. So they don't have to do anything extra to support the protocol. So when you look at rapid spanning tree, it's a very good solution for any application where you have more than one vendor switch on site, because the chances are very, very high, almost 100%, that both switches will support spanning tree. So it's fair to call it the standard redundancy. In fact, multiple vendors will have it turned on out of the box, so that if you do connect their switch to a network, chances are high that it won't cause an issue. Another advantage of rapid spanning tree is that it's a flexible, non-fixed topology, so it can really handle anything you want to throw at it. I've seen many drawings from customers and consultants where there are just lines going everywhere across the screen. And they're like, yeah, we've got 50, 100 connections to everything. That way, there's always a redundant path. However, it is unpredictable in its recovery time. That is to say that if you were to cause a recovery on a rapid spanning tree network 100 times and measure the result, you would likely get 100 different results. It will depend where the break is and of the calculation for all the devices. It's unsuitable for large-scale networks, as large-scale networks with many switches will not be supported. There's a maximum age time of the spanning tree data as it passes through the network. By default, for most devices following the standard, this is 20. It can be set up to 40 and still be standards compliant, but anything beyond that would be outside of the standard. We look at a very simple rapid spanning tree network with just a few switches. You can see here there's a couple of elements to it. The first and most important one in rapid spanning trees calculations is the root bridge. There's always a master in rapid spanning tree, and it's an elected role. So at the start, when you power on every switch, they'll all consider themselves the root bridge and let their neighbors know, hey, I'm the root bridge, I'm in charge, here is my information. And based on this information, one of them will be elected the root bridge, and then every other device will calculate its active connections based on the cost to the root bridge. So if you look at switch B, which is directly connected to the root bridge here, of course, this connection here is going to be active, and the one that doesn't go to the root bridge will not be the active path, because this one is less hops to the root bridge. Of course, this is a simple diagram. There's more to it than that. We'll go into that in the next slide. C also has a simple calculation in that it's directly connected to the root bridge and its other link is not directly connected. So we can see here from the design point of view, these will always be the active links in a normal state. And with regards to A, it may have a more complicated answer to the question which link should be active. Since both connections don't connect to the root bridge, it has to take more into consideration, and we'll cover that on the next slide. Just briefly, Adam, did you want us to do questions during or keep it all to the end?
If you want to answer questions during, mate, that is not a problem. Did you want to publish Michael's question?
Yeah, I just saw Michael's there and thought it might help him out if we answer it now.
Good to answer now, absolutely, mate. Go for it.
Michael, it's exactly as you say. The flushing of the FDB is the deletion of the MAC address table. Depending on the vendor, they call it different things. The forwarding database, the MAC table, or the CAM table is the list in the switch of which MAC address is behind which port. When there is more to consider in rapid spanning tree than just an individual connection and whether it's directly connected to the root bridge, there's a couple of things taken into consideration, including the port ID. So the port identifier means that if you don't manually configure a priority for the port, the lower port number will be used. So if I have two connections going to the root bridge, the one with the lower port number will be active and the one with the higher port number will be inactive. When we consider which device should be the root bridge, you can see here at the start, there's a priority number. If it's the same on every device, the MAC address will be used. But if I was to set the priority lower on one of these devices, it would then become the root bridge. So I can choose the position of the root bridge in my network, as well as which links should be active. On top of that, with regards to the ports, they also transmit the cost of the port. That is, there is a value associated with the speed of the port, which gives it a cost. So if there is a 1 gigabit port and a 100 meg port, the device will use the gigabit port as it has a lower cost than the 100 megabit one, which has a higher cost. That's built in to help define, that faster connections are more desirable to use. For anyone familiar with spanning tree in the past, the earlier editions of spanning tree, if there was a break in the network would stop working and recover, and there'd be a long period of time. One of the optimizations of rapid spanning tree and optimized rapid spanning tree is making decisions more often that cause less downtime. So if we look here, we have a bunch of words on the screen, and apologies that it's so busy. We have a root bridge at the top here with some designated ports. We have some neighboring switches. So these guys have identified this as the root port. That's the port that heads to the root bridge. These roles are very important. It helps the switch decide what it should do in the event of one of those links going down. If we look at the switch at the bottom, is a good example here. It has a root port and an alternate port. The alternate port can be activated if the root port goes down, and the switch will carry on. It knows, hey, I don't need to do too much about this. I know I've got 2 paths to the root. If one goes down, I'll simply use the other. It's a very quick and easy process for the device to move forward. We have an edge port. An edge port is a role assigned to a port that goes to an end device, which is to say the switch sent out some rapid spanning tree information at that port, and it didn't get any back. So its assumption is that must go to an end device. The edge port is important because if this device goes down, the switch won't tell anybody. It's not going to say, oh no, the network's gone down, we need to flush our forwarding databases and recover everything. It just goes, oh, an edge port went offline. That's not a big deal. The backup port here is when the switch has sent out some spanning tree information to see if there's a neighboring switch there, and it received it back itself. So it sent it and then it got it itself. This can happen if it's plugged into a hub or maybe a unmanaged switch or like a 2-port PLC, for instance. In this case, the switch will act much like an edge port. It will block one of the paths to make sure there's no loop. But when it goes down, it will simply activate the other one without having to tell the rest of the network what's going on. In regards to Paul's question, what's the benefit of selecting your root bridge rather than having the network do that? It's more about positioning. Since everyone will calculate the path cost to the root bridge, people will keep their active links directly connected to the root bridge. So if we look at this device here, at the bottom here, it could be that most of the important information in our network is passing between this switch here and this neighboring one. However, based on the fact that root bridge is at the top, this link is being kept inactive. That may be suboptimal in terms of traffic flow. It could be that these, there's 100 switches this way, for instance, and most of our traffic is across here. So by positioning the root bridge in the network and choosing where it's located, we can control which links are going to be active and which ones are going to be inactive. So rapid spanning tree is a simple protocol that's also very complicated. Out of the box for small networks, you can just plug it in and it just works. You don't have to think too much about it. But of course, there are always optimizations. It could be that there are some scenarios where maybe these links, maybe there's 10 switches with 100 meg links and 1 switch with a gig link. And you want to make a decision about which one's more important. Maybe if it's 11 or 12 100 meg links, it's going to go this way, and that makes sense. Maybe if it's 900 meg links and then a 1 gigabit link, for instance, or vice versa, there'll be path cost considerations for which is the better link for your application versus which one's going to be chosen based strictly on the path costs. So to sum up rapid spanning tree, it's nice that it's flexible. It can get a little complicated. And it's very good that it works in multiple different vendors. So if you have multiple vendors, you can connect them together. However, the downside mainly is that depending on where the failure is, if the root bridge fails, for instance, the recovery time is much longer than if the link to an edge port fails, which has no recovery time. So it's variable in the event versus the outcome of recovery. The next one we're going to look at is Media Redundancy Protocol, or MRP, which is an IEC standard based off ring topologies. Because it's a ring topology or a circle, it only tolerates a single failure. It has a guaranteed worst case recovery time. That is to say that no matter where the failure is, you're guaranteed it will recover within this time. That means that you can plan around that. If you have an application that's working on their network and you know that application will keep working as long as it doesn't have a longer than 200 millisecond outage, then you know that no matter what happens in terms of the redundancy, the application will continue going. It has a single role, unlike the root bridge in an RSTP network, which is an elected role. You have a single configured role called ring manager, who's designed to control the redundant path in the network. So his job is to make sure that that redundant path is controlled, and he decides whether that link should be active or inactive. The standard calls for up to 50 devices in a ring. So if you had a large scale network that had 50 different positions you needed to put a switch, it would be supported by MRP and not by RSTP. Hirschman's implementation allows for up to 200 devices. This is to bring it in line with the proprietary solution they had previously. And MRP is a standardized version of what was previously known as Hyperring from Hirschman and Siemens in the past. That there is to give you some confidence. It's been around for a long time. It's very proven, even though it's relatively new. Well, I guess 10 years old now is not that new. So what does it look like? We have here our redundancy manager or ring manager. People will call it different things. He'll send some test frames around the network. It's more or less a small watchdog packet sent very frequently. And as long as that's going around the network and coming back and being received here between switch D and the ring manager knows everything's okay. None of the links are broken. All of the switches are working. All the links are active because I'm getting this back in the same amount of time. If he was to miss 3 of those, he would consider the network failed somewhere and make a decision on what to do next. The link here with the dotted line, for clarification here, between switch D and the ring manager, that link looks like a normal link. So for switch D, that link is up and a normal connection like anything else. On the ring manager's side, though, the state would be what they call discarding. So the ring manager won't forward any data this way. So this network ultimately, it's like that link isn't there. It's a straight line network between the redundancy manager and ending at D. One of the things the redundancy manager does to ensure that the traffic passes around the network so that those 3 little packets that are the watchdog frames are always received back is he sends them with a prioritization value. So he's using quality of service with VLANs to prioritize that information as more important than the rest of the traffic on the network, so that even if the network load is high, those test frames won't be lost. If a break was to occur, such as between B and C here depicted, as soon as the ring manager misses those 3 frames, so he will make a decision and say, okay, I didn't get back my three messages, or I've missed 3 in a row. Something's gone wrong in the network. I need to let everybody know to flush their forwarding database. I need to activate this link, and then we'll recover the network. Depending on the configuration, MRP supports a guaranteed recovery time of 200 milliseconds or 500 milliseconds. And that really controls how often those test frames are sent. If you set it to 200 milliseconds, they're sent every 20 milliseconds. That means that it takes at least 60 to 80 milliseconds for the redundancy manager to realize that this link is broken. And then he'll take corrective action. The corrective action then takes, depending on the size of the forwarding database, how long it takes the switches to clear it, to recover the network. If it's set to 500 milliseconds, then it's sent every 50 milliseconds, and that'll help to control it once again, that it would take between 150 and 200 milliseconds for the redundancy manager to realize he's missed 3, and then he would start the recovery process. So it's still pretty good. And of course, it will always recover then within that 500 or 200 milliseconds. The worst case scenario, if you think about this 500 and 200 milliseconds timers versus the numbers we said, is that it could be that this link is active and no data flows through. Because the switches actually do something really clever as well. They actually have the ability to notify the ring manager. So if switch B has his link go down, rather than just sitting there and not saying anything and waiting for the redundancy manager to do everything, switch B will actually say to the neighbors, to everybody, hey guys, this link actually went down. Like, we need to do something. And when this happens, switch B will delete its forwarding database by itself, and it will notify the rest of the network that it has done so. Switch A, when it sees this pass through, will also delete its forwarding database and continue that along to the ring manager or redundancy manager. And the same happens in the opposite direction. And the recovery time then is, as you can imagine, extremely fast. The longest part of the recovery time using this method is actually detecting that the link went down. So for something like a fiber connection, it's extremely quick. It's almost immeasurably quick how long it takes for the detection process. And then the clearing is also a very, very quick process. Best case, we're talking 1 to 5 milliseconds. Generally speaking, we talk about 1 lost packet and then the network's recovered. If it's a gigabit copper connection, it can take a little longer. It can take up to 50 milliseconds, sometimes even a little longer than that, just to realize the link's gone down, and then it recovers. Still, it's much faster than the worst case scenario of 500 milliseconds or 200 milliseconds. I see Paul's got a question there. In a larger network, would it be good practice to make the ring manager the switch that's furthest away from switch cage to the SCADA? There is certainly a consideration of distance when you calculate the recovery time. But since the speed of data across the network is so fast, it's very much the smallest amount. What we generally advise when someone asks this question is to put the redundancy manager somewhere where people will see it as normal part of operation, because it actually has a notification on the front of it, a little like status light generally, or a terminal that will say everything is fine, I'm getting back my test frames. So just walking past it and looking, you can see that it's okay, and that everything is okay, because if the watchdog packets are being received at the ring manager, then you know that everything else is working okay in the main network from a redundancy point of view. MRP also has the ability to work hand in hand with link aggregation, which means that you can have more than one physical connection for each section of the ring. That means that if you imagine something like a road tunnel, you could have a separate fiber running down both sides and a single set of hardware switches using that as one ring. In that case, in the best case, depending on the fault, you could handle 2 faults. That, of course, depends. If one of the switches was to fail, obviously, you couldn't lose another switch and still handle that fault. But if, for instance, one of the links was to go down, you could still have this other link as active, and the ring would still be in a healthy state, and you'd still have your backup links in the case of a second fault. This also can be used in the other manner, where you can consider these links as a single connection point, and if one goes down, you can force down the other link and use the other path. That's generally when we use link aggregation as a bandwidth solution. So for instance, having 2 sets of 1 gig connections forming a 2 gig ring, or 2 sets of 2.5 gig connections forming a 5 gig ring, for instance. So the advantage of MRP, when you consider it against spanning tree, is namely that you give up having multiple points of failure in exchange for having a guaranteed recovery time. And if the recovery times are too great, we have parallel redundancy protocol. So the parallel redundancy protocol is in simplest terms, sending everything twice, and then if one of them gets lost, we don't care because we have another one. If we just duplicate everything, then if we have one failure, we have no loss of data. The downside of that is obviously you have to spend more money to put 2 of everything in. But if the application calls for never losing any data under any circumstances, then duplicating it is one methodology to get there. It looks a little bit like this. We'll talk a bit about the different devices in this network. We actually have a DAMP. This is a device, an end device that supports PRP. So it actually has built-in support for the protocol and 2 network interfaces of its own. We have a red box or redundancy box, which pretty much is just a switch that supports PRP. So you have multiple end devices plugged into it and it connects to the PRP system. And we also have singly attached nodes, which is a device that plugs into either LAN A or LAN B. These could actually have working devices. It could be that LAN A is an existing plant network. LAN B is put in just to add some extra devices that needed some redundancy. And the application is actually behind the red box and including this DAMP. And it's getting the advantage of using both networks. And if one of them was to fail, the other one's still operating. One of the cool things about PRP is that it's actually stored in an Ethernet frame between the data and the frame check sequence in this RCT trailer. It's cool because data is normally read from left to right to the end of the data and from right to left from the frame check sequence, which means that a normal switch will not see the RCT trailer, which means that the devices in LAN A and LAN B don't need to support PRP. With a little asterisk as always, this increases the size of the frame. So the maximum frame size in LAN A and LAN B needs to be at least 1524 bytes. Otherwise, the RCT trailer could push it bigger than the maximum frame size, and the switches may discard the data. If we look at what it might look like in an application, we could have several DAMPs, dual attached nodes, which are directly connected to the PRP system. So they have a network interface to LAN A and to LAN B. LAN A could be, an MRP ring. LAN B could be an RSTP network. We have SANs or singly attached nodes that connect to one of these networks. These devices in LAN B, the SANs, can see each other and can be seen by the people who are connected to both networks, but cannot be seen by devices in LAN A. So LAN A and LAN B are completely isolated from each other. And any device here behind a red box can talk to both, of course. So you can see that if LAN A and LAN B already existed in an application, adding PRP would not be too big a cost if there was an important enough reason to need to have a guaranteed 0 millisecond solution from the devices down here to the devices up here. Oh, not that guy so much. So, didn't mean to grab him. So from these devices to these devices, there's no recovery time if there's a failure in one of these networks in LAN A or LAN B. There's also some interesting applications for PRP and wireless, where data can travel into a system and the 2 PRP networks, which could be A and B, are actually wireless networks. And so if there is some interruption on the wireless or some loss of packets across there, chances are high that it won't happen on the B network at the same time. And the end result is that the wireless system has a very low latency and feels very similar in terms of its operation to a cabled network. Not so much like a wireless network where you could have very big differences between the transmission time of the data across the network. And this is an early drawing. We actually have a device which supports 2 radios and PRP. So you could just have 2 wireless networks. That's a good question. We'll just flick back and answer that one. What happens if the redundancy manager in an MRP network fails? In this design, the network actually looks like this. Well, we've got RM here, A, B, C, D. And this extra link between the ring manager and D is physically connected, but logically it's not used. From a network topology point of view, it doesn't exist. There's no path there. So if the ring manager was to fail, A, B, C, and D would still communicate without any need for the ring manager. So more or less, if it's not there, it's not needed anymore, because its only job is to make sure that this link is not active. Hopefully that's answered the question. The last interesting redundancy from the standards group we wanted to talk about is high availability seamless redundancy, which I always say wrong because it's a mouthful. And it's more or less a ring form of PRP, is a nice way to think about it, where it simulates two networks by using clockwise and anti-clockwise transmission, and it requires specialized hardware to support. That means every device involved in HSR needs to be a HSR device. It might look a little something like this, where you have DANs and red boxes again, similar to PRP. And this is a dual attached node that supports HSR. So this device has HSR functionality built in, and it has, more or less a port A and port B. And then we have some red boxes, which are switches supporting it on behalf of the end devices. They're acting like a little proxy system for the devices that don't support it to join that network. The HSR tag is put at the front of the frame, which to any non-HSR device would cause issues. So it wouldn't be processed. The data from a device such as this PC here is sent into the red box, forwarded in both directions across this network. And as it passes through and gets sent to the end device, this red box here will keep a track of this, and it will allow it to know when the duplicate comes through and discard that duplicate. So only one copy will be sent through to the end device. This means if there is a failure, say of this device here, the data would still be received by the end device in the same amount of time. There's no impact on the application from a single failure. It also supports coupling to PRP natively in the protocol. So they designed it with compatibility in mind. So a device here could be a HSR PRP coupler, which means it's running HSR on these ports and PRP on the port heading out to LAN B. So it's doing both at once. And they are devices programmed to understand that. So they actually have, both the HSR tag and the RCT tag at one point. But they're clever enough to handle that successfully. When it comes to the redundancy, it's important to check compatibility. In most cases, you're picking a single protocol in most devices. Sometimes you can get away with running multiple protocols, but if we look at things like PRP and HSR and even fast MRP, which is a hardware implementation of MRP, these protocols require specialized hardware, and so you're not generally going to be able to run more than one on a device. MRP is typically software based, and RSTP is chipset supported in most of the switches. And so you'll normally get one instance of RSTP on a device, one instance of MRP. Some vendors will support multiple instances of MRP as well, but it's important to consider when you're putting it in that you have to have something that every device is going to run. Otherwise, you're not going to have redundancy working across the whole network. There's also some solutions for joining different protocols together. However, there are no standardized solutions. The guys at Hirschman have got some proprietary solutions, such as ring network coupling and redundant coupling protocol. which are two different things with very similar names. The redundant coupling protocol we've used with multiple customers, mainly to join different protocols together. So if we had, for instance, one of these protocols supported by the device, we could use redundant coupling protocol to join those two networks together with no single point of failure. And more or less what actually happens is there's a separate RSTP instance running just to maintain these two connections, and the rest of the network is not aware of that. Otherwise, with some of the protocols, such as HSR, you can couple with PRP natively. And with HSR, there's also compatibility with some devices and RSTP for coupling as well. More or less, that's the end of what I had prepared. We'll just make sure that there are no further questions.
Yeah, we've got a few questions, Adam. So in regards to what are the difference between hyperring and MRP?
Okay. It's actually the main functional difference between the two is that if we go back to the MRP portion, this feature, so for the switches in the ring to notify the redundancy manager that there's a failure, is supported in hyperring and is optionally supported in MRP. The MRP standard doesn't say you have to support this feature. It's called advanced mode or link down notification, depending on the vendor's interpretation, and it's optionally supported in the standard. The other advantage the advantage MRP has over hyperring is hyperring uses VLAN 1 always. It's hard coded, you can't change it. So any network with hyperring or multiple hyperrings has to have VLAN 1 across the entire network for correct operation, which gives you a single point of failure. MRP supports customized VLANs, so you can choose which VLANs are used for each MRP ring, and it's recommended to make them all unique. This advantage means that there's no common failure VLAN, if you will, across the entire network or infrastructure.
Yeah, excellent. Thanks, Adam. Michael had another question as well with regards to infrastructure that already has redundant VLANs for each PLC and SCADA connections. So where does PRP benefit over an existing solution?
I assume based on what Michael's saying, he's talking about the PLCs having two network cards going to their own separate VLANs, maybe in separate hardware. More or less, PRP is trying to achieve the same thing. So the advantage only of PRP is that it wouldn't be complex. You could just have it out of the box working that way. But otherwise, you're going to have more or less the same result. Except that most likely in the PLC, unless it's sending data at the same time, it probably is sending it on one card and then sending it on the other if it fails. But if you are coding it to send always on both, then it should be more or less the same outcome. In PRP, however, the duplications will be removed before sending to the SCADA server. So whilst in your solution, you would have both sets of data recorded as being received, in the PRP solution, only the data would, one copy of the data would ultimately end up at the SCADA system.
Cool. And one more question. What industries do you normally see these protocols being used?
The PRP and HSR protocols specifically are mainly being used in the power industry. However, PRP has a lot of niche applications, such as the wireless one we talked about, which is getting use, wherever it's suitable. We've worked with some system integrators who have done SIL-based safety systems using PRP. And we've talked to some integrators who are working on typical mining applications with stacker reclaimers, taking advantage of using PRP so that when the when the fiber slip rings have issues, they have a redundant link in place already to take over the communications. And similarly, when people have upgraded networks, so they have existing equipment that's being put in, some people have used PRP to take advantage of what they're putting in and what they used to have so that they don't have to just pull out the old equipment and sort of throw it in the bin. Outside of that, MRP and RSTP have use pretty much everywhere. So they're not application specific, they're more general purpose.
Excellent. That looks like all the questions. So I'll just give another couple of seconds in case something else comes in. But
worries.
I think that's it, and we're right on time too. So I'll just thank you everyone for joining. The webinar has been recorded, so if you missed part of it or missed it all completely, we'll be sending out the link later today or later this week, where you can rewatch it. And yeah, thanks for attending today. Hope you got something out of the presentation from Adam. If you've got any questions, we'll send out his contact details as well, so you can get in touch with us, and we'll go from there. So thanks again, everyone, for attending, and we'll hopefully be doing more of these webinars next year or this year as we continue. And yeah, hope you get something out of it. Thanks, guys.
Thanks, guys.